Okay, so it's time to begin the fourth lecture. So please start the lecture, Stephen.
All right, thank you. So a bit of a reminder of where we are at the moment. We have this decomposition method based on the cube lemma, which has its advantages and disadvantages over more traditional decomposition methods. So the traditional methods tend to be very computational heavy, but have the advantage of giving lots and lots of information. And this other method based on the cube lemma tends to be much more streamlined. It's quick and dirty and gets rid of a lot of the calculations, but doesn't give you quite as much information. So in the first part of the talk today, we're going to look at how we can take this new method and get more information out of it so that it's closer to the traditional method, but without doing a whole lot of extra work. And in the second part, we'll give an application of that where it will get used in terms of calculating the homology of certain loop spaces. So, so a bit of to set things up, I'll remind you of sort of the general corollary that we have. So if you start with a homotopy cofibration, so let's do that. You have a homotopy cofibration with loop H having a right homotopy inverse. Then you can identify the homotopy fiber of H as loop Z half smash A, and you get a splitting. Loop Y is loop Z cross the loops on loop Z half smash A. All right, but we said nothing about the homotopy class of this map. Right. Well, not quite true. I mean, we knew it came from a certain source. So we know that, I'll call this, say, phi bar, that there's a quotient so phi bar was the quotient of some map phi, where this looked like there was an identity, and then there was some lift to a fiber, and no, okay, let me not say this. So because I think I'm muddling it up a little bit. Okay, so we don't know much about the homotopy class of that mapping. And the goal today is to find out more. Okay, so to do this, we'll go back to the more general setting. So this was, this statement was what we called corollary C. So it came as a special case from something we called theorem A. So let's remember what theorem A was. So it said, suppose you have a homotopy cofibration from A to Y prime, and a map from Y prime to Z, call it H prime, then there's a diagram of, I'll just call it various data. You have the cofibration to start with, and then you have this map from Y prime into Z, and you could precompose with the map to Y and call that H, and take fibers. Okay, so here the columns are homotopy fibrations. And we saw that if loop H has a right homotopy inverse, then you get another cofibration that tells you something about the relationship between E and E prime. So there's a cofibration which starts with loop Z half smash A into E and then into E prime. Now I'll call this map phi bar, where phi bar is a quotient of the composite that you get when you do, you pick a lift G of this initial map F up into E, and then do the action. And you have to pick a good lift, not any one, but a good lift always exists. So you've got in the general scheme of things, you might think, for example, you know things about the space Y, and let's say Z as well. And then you're going to, say, attach a cell to Y and to get a new CW complex Y prime. And you'd like to know something about its homotopy type. And this fibration will tell you something, especially because it splits. So if you already know something about Z, where it splits after looping, then you only have to find out things about E prime. And this cofibration is supposed to say, well, given that I kind of know things on this side of the diagram, I should know something about E. I kind of know something about the map phi, and hopefully that tells you something about E prime and therefore Y prime. That's the philosophy. But this map phi prime is, while it's described in terms of the action, it is sometimes not so easy to get a handle on. And we'll talk today about more being true. In a special case, when your cofibration starts not from a space A into a space Y, but from a suspension into Y. So in the case of a homotopy cofibration from suspension A into Y with cofiber Y prime, you get a homotopy commutative diagram. That better describes this map phi prime. So here's your phi bar. Or it doesn't describe it directly, but a little bit indirectly. So if you go from E back into Y, so you've done phi bar, and then you've gone back down to Y, then you can identify this map. So this half smash, on the one hand, will be homotopy equivalent to, because of the suspension, this will be homotopy equivalent to loop Z smash suspension A, wedge suspension A, and we can identify this map into Y. So on the suspension A part, what happened? Well, phi bar restricted to suspension A essentially comes from this map G, and G was a lift of F. So restricted to suspension A will just recover F. So that's not exciting. The interesting part is what happens to the smash product. And there you get a certain Whitehead product of the attaching map F with some other map gamma. And to describe it, this map from Y to Z has a right homotopy inverse after looping. So we can give that inverse a name. So if S from loop Z to loop Y, if this is a right homotopy inverse, for loop H, then gamma is the map that starts with the suspension of that section and then evaluates on Y. So the extra information you get out of this is that this map that was constructed from a homotopy action has something to do with Whitehead products when you pass from the fiber E back down to this original space Y. And as a corollary of this, if there is a homotopy cofibration, so this will be the enhancement of corollary C, where we start with suspension A to Y to Z. Loop H has a right homotopy inverse. Then we can say more about the homotopy fibration that we get out of it. On the one hand, we already knew that the fiber of the map from Y to Z is loop Z half smash suspension A in this case. And this map will end up being the Whitehead product of a map gamma like this, together with the attaching map, plus the attaching map when it's restricted just to suspension A. The point being that in this situation, we can identify the homotopy class of this map. So not only do we get the homotopy type of the fiber, but we know the class of the map that it's mapping into Y with. So for example, if we go to this class of Poincaré duality complexes that we've been looking at, oops. So we'll let M be one of these n-dimensional Poincaré duality complexes. It satisfies homotopy cofibrations. You have an attaching map for a top cell. And the n-1 skeleton of M looks like a wedge of two spheres and some other space. And if you take the other space into M and take its cofiber, Q, then cohomology of Q is the same as the cohomology of a product of two spheres. So it looks like M has a product of two spheres cohomologically embedded in it. We proved lots of nice properties about this, including the fact that the inclusion of the n-1 skeleton into M has a right homotopy inverse after looping. Okay, now if in our corollary we want, no, I'm saying, like, no. Okay. Right, so if we apply the corollary, we can enhance the homotopy fibration that we had. So when we look at this inclusion of the n-1 skeleton into M and take its fiber, we get loop M half smash the sphere. And that sphere is a suspension. And we can identify the map from the fiber as being some Whitehead product based on F, the attaching map for the top cell of M, and gamma is essentially got to do with the section for the right homotopy inverse. So we get sort of more information out of this, and you get a splitting. So this is a sort of, I can think of this as a sort of Hilton-Milner style theorem. What do I mean by that? So the Hilton-Milner theorem says, if you look at loop suspension X, wedge suspension Y, it breaks up as an infinite product of loop suspensions of smashes of X with smashes of Y. And it tells you that all of the maps from each of the factors, if you take a loop suspension, some number of smashes of X, smash some number of smashes of Y, map it into loop suspension X, wedge suspension Y, that map is the loop of a certain Whitehead product. So it gives you complete information. And in this sense, you get a similar statement. You have a decomposition, and you know, in this case, you have two factors, or depending on how you want to write this, possibly three, if you break it up as a wedge. You know how loop M is mapping into here, and you know how the other factor is mapping in. It's got something to do with a Whitehead product. And so you've got much more information to play with. Now, where is this coming from? So where do the Whitehead products come from? We have this statement which says you've got this map phi bar, which had something to do with the homotopy action of loop Z on E, and it's related in some way to Whitehead products. So you've got two very different things, an action and Whitehead products kind of intermingling. So if we want to find out where these Whitehead products come from, we have to think of both contexts. So they come from joining two different contexts which seem to be distinct, but because they're joining, I guess they're not distinct. Come from joining two seemingly distinct constructions. Okay, so the first one goes back to the action. So we'll sort of step back a little bit from all of the hypotheses in the theorem so that we can just bring them in as needed. So suppose we have a homotopy vibration sequence. We've got some map from Y into Z with fiber E, and let's call this map P. And you've got a connecting map from loop Z to E. And just to be clear here, we're not assuming that loop H has a right homotopy inverse. Not yet. Just have a vibration sequence. We know there's a homotopy action of loop Z on E. And its restriction to loop Z would be the connecting map. Its restriction to E would be the identity. And that, so I think of this as a map, let's see, extending the map from loop Z wedge E into E, given by doing the connecting map on loop Z and the identity on E. Now, if you compose back to loop Y, so if you look at, start with your action, so I'll call it A for action, and pre-compose with loop H cross the identity, then if you restrict to the loop Y factor, that's like doing loop Y to loop Z and then doing the connecting map to E. But that will be going along two steps in this vibration sequence, and that'll be null homotopic. So this, let's call this theta. Theta restricted to loop Y is null homotopic. So there's a factorization through a quotient. Call that theta bar. All right, so this is one appearance of a map from the half smash of loop Y and E into E. And here is a different context in which we'll get a similar map from loop Y half smash E into E. So consider the homotopy fibration diagram. Where let's start with Y wedge E mapping into Y by, we'll do the identity map on Y, and our fibration sequence, there's a map from the fiber into Y called P. So we'll take that map as well. So this is our starting point. If you map down into Z, so again, remember, here's our fibration sequence. This. If we map this down into Z and precompose, oops, then the composite's determined by what happens to each wedge summoned. So if we restrict to Y, we just get H, but if we restrict to E, we'll get E into Y into Z, and that's null homotopic because it's two steps in the fibration. So we get a commutative diagram if we pinch to Y and then do H. All right, and we can take fibers. The fiber of the map H is E, and the fiber of Y wedge E into Y would be loop Y half smash E. So canonically, there's if you start with A wedge B and pinch to A, then the fiber is loop A half smash E. And you get some induced map of fibers called gamma. Now you've got this map gamma from the half smash into E, and this other map theta bar from the half smash into E. So the same domain, same range, and Gray showed that these two maps can be chosen to be homotopic. And the proof involves turning various fibrations into actual, various homotopy fibrations into actual fibrations and such, and writing down an explicit homotopy. Okay. So what this means for us, if we go to this decomposition theorem, decomposition theorem had this map that had something to do with an action. Okay, identify gamma better. So that we can better relate it to the map coming from the action. And we'll see that it's gamma that has something to do with Whitehead products. So let's consider a preliminary case. So thinking of a slightly different context, Ganea showed there's a homotopy fibration where if you start with a wedge of two spaces and you include it into the product, then the fiber is loop x1 join loop x2. And the map from the fiber to the wedge is a Whitehead product. We'll call it the Whitehead product of two evaluation maps, where this first one would be do suspension loop x1, evaluate to x1, and then include into the wedge. And same thing for the other evaluation map. Okay, the point being that we have a situation where we've identified a fiber into a total space as a certain Whitehead product. So let's use that to identify a different fiber. So let's see. So we want to use this to identify the map from the fiber in context of looking at a pinch map from x1 wedge x2 into x1. And its fiber, loop x1 half smash x2. We want to throw an extra condition on that one of these spaces is a suspension, but we'll get to that in due course. Okay. So the first thing to observe is that there's a lift. So if we take x1 wedge x2 and we look at this Whitehead product of evaluation maps and pinch to x1, then because this Whitehead product is determined by these two maps, and this one composes trivially to x1, the naturality of the Whitehead product says that this composite will be trivial. So we'll end up with a lift to the fiber. And now let's suppose that x2 is a suspension. Then we'll get the following. So we'll get our lift, let's call this lambda. And we'll remember that this is now loop x1 join loop suspension x2 bar. And we can pre-compose with the suspension map. Okay. And on the other side, let's this is loop X1 half smash suspension X2 bar. And this breaks up as loop X1 smash suspension X2 bar, wedge suspension X2 bar. And we could pinch to the first wedge summand. And with a little bit of work, you can show that this composite ends up being a homotopy equivalence. On the other hand, when you look at what have we gone here? So let me rewrite this. So we get, let's see. If we think about writing some of this down again. So here's, this is just this fiber of the pinch map. And we have this lip lambda. And we've pre-composed with loop X1 join X2 bar. Let's write a suspension X2 bar. And this thing, grief. So on the one hand, what do we have? So if we go this way round, then this part is homotopy equivalent to this one. And then we map it into the wedge. But this way round, we get a Whitehead product pre-composed with some map. So it's still a Whitehead product. This would be the Whitehead product of the evaluation map on the first factor, composed with the evaluation map and the suspension, but that's be the same thing as including into the second summand. And it tells us that when we look at this fiber, well, the suspension X2 bar part is just going to be include in to the second wedge summand. And now we've seen that we can take this part mapping in as this Whitehead product. So we get a fibration where we take the pinch map and get a fiber that's got something to do with the Whitehead product. So this is this is an evaluation map, and a Whitehead product based on an evaluation map and an inclusion. Okay, so we used, the point of all this was to use Guinéa's result to identify this other fibration as having something to do with Whitehead products. Now we can go back to our case. So we've got this homotopy cofibration, suspension A to y prime. And then we've got a lift. So we had a map from Y into Z with fiber E. And F is lifting by some map G, and we get a little bit of leeway in choosing G. So if we pull some different strands together, we had this construction of a map gamma where we took Y wedge E and mapped it to Y by doing the identity on Y and the fiber map from E to Y. Map it down to Z. That was the same as pinching to Y and doing H. And we got this map gamma that we're trying to identify. Right. Well, we won't identify gamma itself, but we will if we back it up a little bit, because this, we have a fiber of the pinch map, and we know how to identify this map when E is a suspension. Right now, generally, E is just some fiber, right, in this vibration, and it won't be a suspension. So we have to adjust a little bit by just precomposing. So we'll map in by Y wedge suspension A via Y wedge this lift G. And the bottom square is natural. We could just pinch, and we get the naturality of this construction would give us a vibration diagram. Right. On this side, we can identify that fiber because we have a pinch map where one of the wedge summons is a suspension. So this we can think of as being an evaluation map, and the inclusion of suspension A into the wedge adds to that inclusion. So what does this give us? This says that if we go this way around the square, or the diagram, if we get some information on gamma, at least indirectly, up to precomposing and composing with something else. That would be the same as going this way around. And this, restricted to the suspension A, we include into the second wedge summoned, then do this map G into E, drop it back down to Y, but that's doing the map F. And then we have the Whitehead product of an evaluation map and this inclusion. And then the naturality of the Whitehead product would say that would be the same thing as doing this evaluation and its Whitehead product with F. Okay. Now, so far, we have not yet used that we're going to assume that loop H has a right homotopy inverse. right? So now we do. All right, so this map gamma, just for generic reasons, has something to do with Whitehead products. Okay, and now we'll adjust it by assuming that loop H has a right homotopy inverse. Well, what does this mean? So remember, we had this action of loop Z on E, and then we backed it up to a map from loop Y cross E. This was loop H cross identity. And if we restrict that to loop Y, it was trivial. And this was what we were calling the map theta bar. Okay. Well, we can refine this a bit now. If loop H has a right homotopy inverse, then when we look at this action and we restrict to loop Z, it will be trivial because loop Z into E would be the same as first going back into loop Y and then going into E. So we could adjust the quotient map and then we can adjust the choice of theta bar. And if we do that, now we go back to this composite upstairs and look at what it's saying with respect to gamma. Okay. Theta bar here, so Gray told us that this was homotopic to gamma. Right. So now if we were to take loop Z half smash E and map it in by the section half smash the identity, then in this lower direction, this composites the identity, and then we're just doing A bar. So if we do gamma composed with S half smash the identity, we get A bar. All right. Now put all these pieces together. If we look at P composed with gamma, composed with 1 half smash G, composed with S half smash 1, lots of bits and pieces, then on the one hand, we could swap the order around because the S and the G are working on different factors. And this becomes P composed with the action composed with 1 half smash G. And on the other hand, we saw that the first 3 terms had something to do with a Whitehead product. And this, again, the naturality of the Whitehead product would mean that we can pass the map S into here. And if you remember, we had this map gamma, which was do the suspension of the section and then evaluate. So this would be gamma taking its Whitehead product with F, composed with F. And then we get it equal to this business. And the latter 2 maps here was really how we defined what we were calling phi bar. In other words, in this cofibration, if we take E and map it back down to Y, and so do phi bar and P, that's this part, that's the same as some Whitehead product. And the attaching map. Okay, so that's where all this is coming from. We end up with this nice statement that says in our main theorem, scroll back to some distance long ago. In our main theorem A, right, we end up with this cofibration that we want to use to help to describe the homotopy type of E prime, because that will help describe the homotopy type of Y prime. In order to describe the homotopy type of E prime, it's helpful to know what this map is doing. On the one hand, this has something to do with an action, and that may be useful in certain contexts. And what we said is that not directly, but if you take this map and reflect it back in Y, then that looks like Whitehead products. Right? So it does give you some kind of extra control over the maps that are appearing. And this is all happening kind of very generically, so that when you apply it in the context of this corollary, for example, with no extra work, you get that the fiber, if you start with a cofibration where the map on the right has a right homotopy inverse after your looping, then not only can you identify the homotopy type of the fiber, you can also identify the homotopy class of the map from that fiber back into the total space. And in so these practical decomposition examples, this can be handy if you know something about Whitehead products. They tend to be easier to work with, particularly when you look at loop spaces and this sort of decomposition, because you can look at the adjoint of those Whitehead products, and that's Samuelson products, and these behave very nicely with relation to loop space homology, for example. Okay, so I'll stop there for the moment.
Okay, so it's about time to restart the lecture. Could you start, Stephen?
Okay, so I will start perhaps by apologizing for the last hour, because while the connection to Whitehead products is important and useful, I've never been able to explain it well. So, but now that we've stated it and thought about it some, we'll use it in an interesting way to say something about the homology of certain loop spaces. So we'll look at the homology of loops on some of these Poincaré duality complexes. Okay, so we'll think again of M being in this class of Poincaré duality complexes that we've been playing around with. And the goal is to calculate the homology of loop M, but as an algebra. So generically, we have this decomposition. If you had any decomposition of loop M as, say, a product of spaces xi, then you would get a corresponding decomposition in homology as a tensor product of the homology of the spaces xi, where I'm taking enough field coefficients or whatever to make sure that there's Kunith isomorphisms. Okay. However, this is an isomorphism as modules, right? Because this homotopy equivalence happens at the level of spaces, not necessarily as H spaces. So the decomposition that you would get in homology would be as modules, or as modules over the Steenrod algebra, or the dual Steenrod algebra, because we're taking homology. It would respect co-algebra structure, but it wouldn't respect any algebra structure. Okay, so we have a legitimate goal here when we say we want to calculate the homology of one of these loop Poincaré duality complexes as an algebra and not just as a module coming from the space level decomposition. Now, in a sense, this is a backwards thing to do. If you remember the traditional approach to homotopy decompositions, if you want to decompose the loops on some space X, then the first thing you do is calculate homology and try to use it to help predict a decomposition. We're going backwards. We're going to start with the decomposition and then use it to help calculate homology. Okay, so to get going, we've got the Bott-Samuelson theorem, which says that if X is a path-connected space, then the homology of loop suspension X is isomorphic as an algebra to the tensor algebra on the reduced homology of X. And again, maybe you want to take field coefficients. So I'll assume throughout that we're taking field coefficients. And the suspension map from X into loop suspension X, which is adjoint to the identity map on suspension X, this induces the inclusion of the reduced homology of X into the tensor algebra. And there's an extra statement which says that if X is itself a suspension, then this isomorphism can be upgraded to one of Hopf algebras. Okay, so this is classical stuff. And here is the statement that we're after. So suppose you have a homotopy cofibration from suspension A into suspension Y into Y prime, So generically, we were thinking about cofibrations of the form A to Y prime, back for theorem A, for example. And then we changed A to a suspension to say something about Whitehead products. And now we're going to change the middle space to a suspension as well. So suppose you have a homotopy cofibration of this form, where loop H has a right homotopy inverse. Let's let F tilde from A into loop suspension Y be the adjoint of F. And let's let R be the image of that adjoint in homology. Then there is an algebra isomorphism. We can work out the homology of the loops on the cofiber. It'll be isomorphic to the tensor algebra on the reduced homology of Y, so the homology of loop suspension Y, quotient out by the two-sided ideal generated by R. Okay. And as an extra remark, if Y is a suspension, so that the Bott-Samuelson theorem holds as Hopf algebras and not just as algebras, then this isomorphism is also as Hopf algebras. So we'll get to some examples later, but you would have something like, so we have cases of simply connected four manifolds, say, where you have a three-sphere attaching to a wedge of two spheres, both are suspensions, passing to the cofiber, which is the simply connected four manifold. The inclusion of the wedge of two spheres into the four manifold has a right homotopy inverse after looping. And this would tell us that the homology of the loop on that simply connected four manifold is isomorphic as an algebra to a certain tensor algebra quotient out an ideal. All right, so we'll get to the examples in a little bit, but let's work out why the theorem actually works. So this will come in several steps. And the first is, if we look at looping this map H, then if we take homology, the homology of loop suspension Y by the Bott-Samuelson theorem is the tensor algebra on the reduced homology of Y. And again, I'm taking field coefficients everywhere. Do loop H in homology to land in the homology of loop Y prime. This is an algebra map. And we're assuming that loop H has a right homotopy inverse. So loop Y retracts off loop suspension Y, and that means that the image of loop H in homology is an epimorphism. So that's just an initial observation. The second, let's think about the adjoint. So this adjoint F tilde from A into loop suspension Y, we can think of it as a composite where you start with A, do the suspension into loop suspension A, and then do loop of the attaching map F into loop suspension Y. Okay. So let's consider if we look at F tilde into loop suspension Y, and then do loop H prime, and we claim that this is no homotopic. Because F tilde is the same thing as composing through loop F, and loop F and loop H prime are two consecutive steps in a vibration sequence. So loop H prime composed with F tilde is triggered. So what does this tell us? Well, in homology, the image of F tilde, so this was the definition of R. So as R is the image of this adjoint in homology, and loop H in homology is an algebra map, we'll get a factorization where if we look at what loop H is doing in homology, so it's this mapping from loop suspension A, its homology is the tensor algebra on the reduced homology of Y, mapping to the homology of loop Y prime. It will take anything in the image of this adjoint and send it to 0, and it's doing that in a multiplicative way. So it will factor through the quotient where you quotient out by the two-sided ideal generated by R. So I'll give names to these maps. You get a factorization like this, where A is just the quotient map. And the factorization will imply that B is also an algebra map. And because loop H star is an epimorphism, so is B. And the claim is that B is an isomorphism. And so that was the statement of the theorem. The homology of loop Y is isomorphic to this tensor algebra, quotiented out by this two-sided ideal generated by the image of the adjoint, and that isomorphism is as algebras. So this, we want to show that B is an isomorphism. Well, to do that, let's find a map that goes in the other direction and then compare. So now we'll aim for another factorization where we start with loop H again. And this quotient map, get rid of the two-sided ideal generated by the image of the adjoint and look for a map in the other direction. Okay, now how are we going to get this? We'll get this using the Whitehead product information from the first half of the talk. So to make that clear, we've got this homotopy cofibration from suspension A to suspension Y to Y prime. And loop H has a right homotopy inverse. So by the enhanced version of corollary C, which was essentially what we were talking about in the first hour, we get a homotopy fibration that lets us identify the fiber of this map H as loop Y prime half smash suspension A, and the map is this Whitehead product and the attaching map, where gamma is we've got this section for loop H, and then evaluate the suspension Y. Okay. Now, what does this do for us? Now think of looping this. We've got the loops on loop Y prime, half smash suspension A. So let's write that as a wedge. Mapping to loop suspension Y, and then off into loop Y prime. Well, on the one hand, the fibration that we got out of this split. So we've got loop suspension Y is homotopy equivalent to loop Y prime across the loops on all of this stuff. And that gives you an algebra decomposition, not algebra, it gives you a decomposition in homology. So we'd have the tensor algebra, reduced homology of Y is isomorphic to the homology of loop Y prime, tensored with the homology of this complementary factor. And this is an isomorphism, not as algebras again, but because this map is multiplicative, it would be an isomorphism as right H star of loops on loop. An isomorphism as right A modules where A is this thing. Now think of looking at what's going on in loops of loop Y prime slash suspension A, suspension A, this tensor algebra, and then do the quotient into the, where you take out the two-sided ideal generated by the homology of the adjoint of F. We'll give this map a name. So chi here, right, is the loops on some Whitehead product. Well, if you restrict this map to the suspension A part, then what happens? So this is an algebra map. So it's determined by what happens on the generating sets. Now this is a suspension. So we could include it in. So determine what happens when precomposed with this suspension. And when we precompose and restrict it to A, then where's the map kind? So restrict it to A, it's really just coming from this restriction to loop suspension F, and that's really just the adjoint. So chi here restricted, chi composed with E, restricted to A is just this adjoint, and when we look at what happens in homology, when you compose with this quotient map, well, R by definition was the image of that adjoint. So if you do this quotient map, precompose with chi and homology, and you restrict to A, you just get the zero map. And if you look at chi composed with E and you restrict to loop Y smash A, so we're just looking at this part. Well, chi on that part is coming from this Whitehead product, taking its adjoint, so you have a Samuelson product. And it's the Samuelson product of maps. It would be the Samuelson product of the adjoint of gamma and the adjoint of F. Or gamma composed with a suspension. So let's, I don't want to, let's just call it, gamma. So for some map, gamma prime. But now, when you look at what happens in homology to this thing, A is an algebra map. So that would go to A composed with gamma prime star, A composed with F tilde star, and Samuelson product now is commutator in homology. But we've already seen that this is zero. So we take a commutator with something that's zero, and that will also be zero. Now, backing up, what does this say? If we look at this map, this composite in homology, it's enough to see what's going on when you restrict to the generating set, because they're algebra maps. And when you do so, you find that on both parts of the generating set, you get the zero map. So therefore, A composed with chi star is zero, which means what? Now you go back to this tensor algebra, decomposed as right M modules for this M via this decomposition. And when restricted to M, it composes trivially with A. So that means that this tensor algebra, when you do this quotient map, you can multiplicatively remove an ideal generated by this part of the module. So you end up factoring through only that part of the homology. So out of this, we get a factorization from the tensor algebra on the reduced homology of Y to the homology of Y prime, this quotient, get some factorization like this. And the factorization implies, because A and loop H star are both algebra maps, so is C. And because A is an epimorphism, so is C. Okay, so backing up, let's just remind ourselves where we are. We had one factorization that just came from generic information from the fibration, right? We quotient out by the image of an adjoint, and that adjoint composes trivially with loop H, so we get a factorization like this. On the other hand, using the Whitehead product information that came from the first part of the talk, we're able to show that you get a factorization in the other direction. And now we can compare. This would be step 4. And we end up with let's think of the composites we've got. The tensor algebra on the reduced homology of Y, quotiented out by this two-sided ideal. We could go into the homology of loop Y prime, and then back out to the tensor algebra, quotiented by the ideal, and then go back into the homology of loop Y prime. Well, C and B, these are both algebra maps. And both epimorphisms. So that says that when you look at the composites, E composed with C and C composed with B, these are algebra maps and epimorphisms. Now, B composed with C, so first do C and then do B. So that's a self-map of this tensor algebra quotiented out by an ideal. And C composed with B is a self-map of the homology of loop Y prime. Both are epimorphisms, right? So if you have an epimorphism, a self-map from a finite type module, which is an epimorphism, it must be an isomorphism. This is module isomorphism, right? But they're also algebra maps. So they're algebra isomorphisms. Right? In particular, we end up with the homology of loop Y prime being isomorphic as an algebra to this tensor algebra on the reduced homology of Y, quotiented out by this ideal. Right, so that was the argument. So we had this cofibration start with the cofibration that's a map between suspensions, take the cofiber, assume the map H has a right homotopy inverse after looping, then you can work out the homology of that loop on that cofiber as an algebra, and it's a tensor algebra modulo relation. Or modulo an ideal. So for example, suppose M is in this class Mn. So we've got homotopy cofibrations where M is in n-dimensional Poincaré duality complex. So we attach the top cell, and the n-1 skeleton looks like a wedge of two spheres, wedge some other space. And if this other space includes into M, it has cofiber Q, then the cohomology of Q looks like the cohomology of product of two spheres. Again, M looks like it has the cohomology of a product of two spheres embedded inside it. Right. To apply the previous theorem, we want a map of suspensions, which doesn't itself, the map doesn't have to be a suspension, but the domain and the range have to be. So we need to an extra hypothesis that J is the suspension. So if J is the suspension of J bar, then what else? We also know that the loop on this J has a right homotopy inverse. So we get an algebra isomorphism that describes the homology of loop M as the homology as the tensor algebra on the reduced homology of the spaces appearing in the n-1 skeleton. It's shifted down one because they're thought of as suspensions. Quotiented by some ideal R, where R is the image of the adjoint of F in homology. And there's an extra note here that F itself is a map from a sphere. So when you take its adjoint, it's also a map from a sphere. It's a map from an n-2 sphere into the loops on this wedge. And its image would just be some single element. So let's let R be the image of F tilde in homology. So R is just a single element. In the homology of that suspension. So it's a single element in the tensor algebra on the reduced homology. So the homology of loop M, I think it was this tensor algebra. and you're going to quotient out an ideal generated by a single element. So quotient out by a single relation. And these things are called one-relator algebras. So just quotient out by a single relation. For example, if you were to take a more concrete example, right, and this would be just a special case of the previous example. So let's take M to be a connected sum of products of two spheres. And we're going to assume that all of these spheres are all of the spheres are at least simply connected. Now M is a Poincaré duality complex. And it's a special case of one of these, this class of Poincaré duality complexes that have good loop space splittings that we've been considering. If we write down the relevant data in terms of cofibrations, then the attaching map for the top cell would map into the n-1 skeleton of M, which would be a wedge of the ingredient spheres, where F is going to be a sum of Whitehead products. So I've got iota mi it's a sum of the Whitehead products that produce the product in each of the pairs of spheres. Okay. So let's see. So let's think about homology. So if we take the adjoint of F, we get an n-2 sphere mapping into the loop of this big wedge of spheres. And we can take its homology. Homology of the loop on this wedge. It's the loop of the suspension, so it's a tensor algebra on the reduced homology of wedge of spheres. And let's write that as a tensor algebra on elements, say U1 up to UD, V1 up to VD, where the degree of UI is mi-1, and the degree of VI is n-mi-1. So the U's corresponds to the mi spheres, and the v's correspond to the n-mi spheres. Then this adjoint, if we look at what it does to this class the generator in the homology of Sn minus 2, it just takes it to a sum of brackets. So we end up with the homology of the loop on this connected sum is isomorphic as an algebra to tensor algebra on this explicit list of generators modulo the single relation that's given by this sum of brackets. Okay, and if each of the spheres is bigger than or equal to 3, so it's a nice suspension in its own right, then this is an isomorphism as Hopf algebras. There's been some interest in this type of homology. So Berglund, a few years ago, proved a statement like this, except it was only for rational homology. So he got this algebra isomorphism, homology of a connected loop on a connected sum, looked like a one-relator algebra, but that was homology with rational coefficients. This works for homology with any coefficients. And it applies much more widely, not just to the loops on these connected sums, but to all of these Poincaré duality complexes that belong to these families Mn, for example. So I guess the interesting thing about this calculation is, well, the end calculation, of course, is interesting, but you somehow got it by doing something backwards. As I said, normally you want a loop space decomposition. The first thing you do is calculate its homology and then use that to predict the decomposition. Here we start with the decomposition and use it to calculate homology. And the way we did it involved knowing this extra information about Whitehead products that were coming out of the decomposition theorem, because they played this really important role in getting this map from the homology of the loop of the cofiber that we care about to a tensor algebra modular relation. So there was one obvious map there was an obvious map in one direction and a not so obvious map in the other direction. And the not so obvious map was the thing that came from knowing information about Whitehead products. So somehow you've got things about spaces, things that you know about spaces first, implying homology rather than going the other way around. So it's kind of a neat flip of the usual way of thinking. I'll stop there. Thanks.
Thank you. Is there any question or comment? No? Okay, so tomorrow is the last lecture, and it will start at 4 p.m. as usual. Thank you, Stephen.
Okay, thank you.